An essential part of any kind of analysis is to see the data in your eyes, to really understand that data. In many cases, this is going to use graphs or tables of the data. But when you're working in a GIS, you're working spatially, you also have a map of the data. Maps offer a simple and intuitive way to visualize patterns and trends in your data that might sometimes be hidden in data or databases. But I think it's worth mentioning. Sometimes using a graph or a table of data is also an effective way to show your results, even when you're working spatially. If you find that using a line graph shows the trends in your data better than using the maps, then use the line graph. It doesn't matter that we're working spatially and all of our data is mapped. Much of spatial analysis is concerned with finding ways of summarizing characteristics of spatial distributions. So we might be mapping at individual point locations using a dot map. This immediately gives a visual presentation of where the points are located, how they're distributed within that data. You can pick out any obvious patterns of events, such as clusters. In almost all cases, when you're looking at your data, particularly with reference to clusters, you need to be careful of your choice of study area. The boundary that you use will affect the patterns that you see within that data. Let's look at a very simple example. You might say that the distribution of points that you're seeing here is random. However, if you effectively take a step back from that data, we increase the study area, now it looks as if the points are clustered. It's exactly the same data, mapped in exactly the same locations, it's just the study area boundary that's changed. So the boundary locations that we use can mask patterns in our data, whether we're just mapping the locations or whether we're using a more sophisticated statistical approach, and we'll look at some of those later this week. So considering your study area carefully will help your analysis, but you still might find that dot mapping isn't suffice. You find that intuition can be misleading, and you may find it difficult to pull out the patterns within that data. You might have a very large data set. You may have a lot of points, and they may have coincidence points, so you can't pull out all the information. Well, there are a number of different techniques that you could use to actually deal with some of those issues with the dot maps to better pick out the patterns. Or you might want to analyze the data further. One frequently used approach to seeing patterns across a whole area is to map intensity rather than just the point patterns. Kernel density estimation measures the intensity of a point pattern based on sample observations. It creates a continuous surface that shows the density of features or values irrespective of arbitrary administrative boundaries. Kernel density can be used to look at the intensity of events, but it can also incorporate the value at those locations, not just the locations themselves. It can also be valuable to actually compare between intensity of different events. So for example, you could compare disease cases with a control group. So effectively look at those who have a disease compared to those who could have a disease. So some people argue that surfaces such as these density surfaces are arbitrary because changing the classification scheme changes the map. Well, it's absolutely true to say that changing your classification scheme will change how the map looks. But let's look at the concept of classification a little deeper and question if it really is something arbitrary. By classifying data, you're grouping similar values together. It's a way of summarizing the data. So this is going to allow you to see patterns within your data. But the choice of classification scheme should be based on the data distribution itself, not arbitrary, but rather an informed decision led by the phenomena that you're studying. The Jensen's natural breaks is an optimizing method that uses data clustering. If you use an equal interval classification scheme, that tries to ensure that the difference between the upper and lower value in each class remains exactly the same. So if we have data that conveniently ranges between $1 and $100 and you divide it up into 5 classes, then each class shows the values that span the same difference in values. In this example, it's going to be a $20 difference. If we contrast that with using quantiles on the same data from 1 to 100 divided up into 5 classes, each class will be showing 20% of the data. So with equal intervals, the interval range in your data remains the same. So in some of the classes you're going to have a lot of data values, in some of them you might have very few, or you may even have none. But with quantiles, the number of values in each of your classes remains exactly the same. It's the range that's going to differ. So all these classification types show different things. The information that you want to share would be different in each case. So it kind of makes sense for your map to be changing. Picking a classification scheme should be part of your data and should be based on the analysis that you want to be doing, and is part of you telling your story effectively. It's part of the skill of communicating your results from your analysis. Good spatial analysis should be carefully designed, use appropriate techniques, and be effectively communicated.